In this video, what I want to do is I want to go over one more example of induction. We're going to do a few more, but in this one, what I want to do is I want to prove that, actually there's a little bit of setup here, but I want to prove that n factorial is greater than or equal to 2 to the n for all n greater than or equal to 4. So this is going to be a little bit different than the example that we did last time. The example that we did last time was a statement that was true for all n greater than or equal to 1. Here our base case is going to be n equals 4. And just to be sure that we're all on the same page, I want to just take a second and talk about this factorial function. N factorial is defined as n times n minus 1 times n minus 2, all the way down to 1. And it's the product of all those terms. So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. So that's what the factorial is, and then just by definition, by default, there's good reasons for this that we'll talk about when we get into counting, but 0 factorial is defined as 0. 0 factorial is defined as 1. And again, we'll get into that when we get into the combinatoric section of our course. But with that under our belt, so this is called the factorial. With that under our belt, I want to prove that n factorial is greater than or equal to 2 to the n for n greater than or equal to 4. And so we're going to have two parts to this. We're going to have a base case. Our base case is just checking that this statement is true when n is equal to 4. And indeed, when n is 4, n factorial, so 4 factorial, is 4 times 3 times 2 times 1, which is 24. And so 24. And 2 to the 4 is 16. And of course, 24 is greater than 16. Great, so the base case is true. And for the inductive step, what we're going to do, so for the inductive step, we're going to assume that the statement is true for some k that's at least 4. So let's assume that k factorial is greater than, did I say greater than or equal to? Let me just make let's be consistent here. So I want to assume k factorial is greater than or equal to 2 to the k for some k greater than or equal to 4. Again, I'm picky about the word sum. If you say for all k greater than or equal to 4, then this turns into circular reasoning. So it's important that I use the word sum here. So we'll assume k factorial is greater than or equal to 2 to the k for some k greater than or equal to 4. And then we want to show, remember this assumption, by the way, is called the inductive hypothesis. And then we want to show that k plus 1 factorial is greater than or equal to 2 to the k plus 1. And that's our goal. And if we can do that, we win. We've established that this is true for all n greater than or equal to 4 using the principle of induction. So let's just do this. So let's look at the thing that we want to prove something about is k plus 1 factorial. And somehow from this, we want to extract information about k factorial. And the way that we can do that in this case is just notice that k plus 1 factorial by definition is k plus 1 times k minus 1 all the way down to 1. And in this term, if I just don't look at the k plus 1 term and just look at the rest, this k times k minus 1 all the way down to 1 is k factorial. So this is really k plus 1 times k factorial. Okay, and by definition, or by assumption, by our inductive hypothesis, k factorial is going to be greater than or equal to 2 to the k. So that means that k plus 1 times k factorial will be greater than or equal to k plus 1 times 2 to the k. If I just take this inequality and multiply both sides by k plus 1, we get this inequality. And what we want is we want this to be greater than or equal to 2 to the k plus 1. And so we're going to do what most mathematicians do and just check if that's true. And if it just happens automatically, then we're done. If it doesn't just happen automatically, we have to work a little harder. So we just want to know, is that greater than or equal to 2 to the k plus 1? And sometimes because we're asking a question via this inequality, we like to put a little question mark over the inequality. So we want to know, is k plus 1 times 2 to the k greater than or equal to 2 to the k plus 1? And so we have to figure out when would that be true? Is it true in our case? And let's think about this for a second. So let's think about this. So first we can cancel the 2 to the k's. I can divide the right and left side of this inequality here by 2 to the k. And when we do that, this is equivalent to saying that k plus 1 is greater than or equal to, let's see, if I take 2 to the k plus 1 and divide by 2 to the k, we get 2. And so is that true? Is k plus 1 greater than or equal to 2? Well, one more step. That inequality is obviously equivalent to whether k is greater than or equal to 1. And is k greater than or equal to 1? Yes, because by our assumption, we're assuming that k is at least 4. In particular, it's at least 1, and everything is fine. So k plus 1 times 2 to the k is in fact greater. This is a valid inequality since k is greater than or equal to 4. And we're done. So that means that we can stop. There's our inductive proof. We've established exactly what we wanted, that 2 to the n is less than or equal to n factorial for all n greater than or equal to 4.